In practice, they often do push them all to the front of the block because that's kind of an intuitive place to put them, but they don't have to be. Yeah? You mean these, D and E and so on? Yes, they're redundant, and in fact, the original papers about, so the question was, are these labels necessary? Could you just not figure it out that I3 must have come from that block because it's in that block, essentially? And the answer is yes, you can, you don't need them, and in fact, the early papers on SSA don't put them in. They just kind of, and then the order of these things doesn't matter, and you kind of reconstruct the semantics from doing exactly what you suggest, kind of looking backwards. I'm putting the labels in for two reasons. One, it makes the operational semantics much easier to write down when we try to define what it means. And second, LVM does this as well. And that's because it's really good documentation. So you can, if you're trying to debug your compiler, you'll notice that these are all the predecessors, and then it'll even list for each block what the predecessors are, so you can kind of line things up. In principle, you don't need them, but in practice, it's really useful. Sorry? This is also getting, so there's another question here, which is kind of related to what Simon was asking earlier, which is, what is the semantics of these phi nodes? And it turns out that you do have to execute them atomically. I'll get to that in just a few minutes. Okay, so this is great. We could turn an imperative imp style program like this into SSA form like that. Actually, Andrew Appel has a great paper from, I think, 1998 or something like that called SSA is Functional Programming, where he basically lays out this connection between pure functional programs and SSA form. So you can kind of rewrite this control flow graph by thinking of each of these blocks as a function that takes some arguments, which are the free variables, the variables in scope in the block. And you can think of these phi nodes as the arguments to the functions at various points. So I'm not going to go into it now, but if you're curious, look up that paper, and it gives a very nice, in fact, I picked this graph, or a variant of the graph in that paper, so you can look at the connection. But you can sort of rewrite SSA-style control flow graphs into pure functional programs, but the trick is that you need nested functions in order to get the scoping to work out. So you need to be able to nest lambdas. And as we'll see, actually where you put the phi nodes corresponds to a nesting of the functions, and then you can define an optimal nesting, which sort of gives you the best way of doing that. And that's the phi node placement algorithm that we'll talk about later. Okay, so a little bit more about this. So this yields an efficient representation. As Simon was getting to, it simplifies some of the representation in the compiler because it gives you this def use information you can look up, given an instruction, directly what its arguments, what SSA variables it depends on, and vice versa. There's one subtlety, though. In practice, you can't always do the transformation I just showed you, right? Sometimes you have programs that do manipulate pointer-fold data, right? They take these SSA UIDs, these local identifiers, don't have addresses of any kind. And so, of course, in any programming language where you can take the address of some piece of data and manipulate pointers, you can't necessarily convert directly into SSA form like this. So, just as a simple example, if you have a local variable x in a C program and you take the address and pass it to some function, that variable's address escapes. You would not be able to register allocate that variable, and so you need to have mutable state kind of off to the side as well. On the other hand, LLVM gets a lot of mileage out of the idea that you can take some mutable state, like some local variables, and promote them to registers. So that's in fact how it goes from the big version of factorial, where it has all the loads and stores, to the very simple version, well, the simpler version where there are only registers. And I'll talk more about that as we go as well. Okay, so that's kind of practice. Sure.
So you get all of these programs from this slide in V-?
Sorry, So, okay, sorry, no. This program, you mean the ones with the addresses? So in V- you cannot, or I haven't fully defined V-, but you would need to have some notion of a pointer. There are, I should say, some kind of research papers on what's called full heap SSA form, where they try to put all of memory into this kind of SSA form, but it's very unwieldy and doesn't really work in practice. So all the kind of modern compilers like GCC and LLVM use this. Basically, you think of the SSA variables as the infinite number of temporary registers that you use to generate efficient code, but you also have standard malloc, load, store, stack allocation, and so on for the imperative data structures in your program. Okay, so what I'd like to do now is drop into a little bit of Coq code, hopefully go a little bit quickly through the basic definitions of how you would set up V- style program, this V- style programming language in Coq, and then we'll talk about the operational semantics. So I haven't made all of this code available yet. I'll put it up sometime later today and give you a pointer to it. But let me just drop over to here. So this is just a Coq file that defines a data type for representing V- programs. And as you'll see, we'll have to add a fair amount of infrastructure on top of this to specify what is a well-formed V- program, what is a control flow graph, what is how are all these concepts connected to one another, and then spell out the well-formedness property, which has to do with the scoping of these UIDs. Okay, so I don't want to go too much into detail, so I'm going to let you read this later at your leisure, but basically just say that we're using Coq features to basically write down data types for those control flow blocks, control flow graphs that we just defined. So we need some notion of the labels on the control flow blocks, some notion of the UIDs, some notion of the addresses. So V- will have imp-style global integer mutable states. So you can have the address of an integer and you can load and store it. Those are sort of there to say that there's part of the memory that's not an SSA form and give us a little bit of wiggle room that way. And all of these things are just atoms, which are essentially natural numbers that you can generate fresh atoms whenever you need them. The only values we have in V- are defined by the natural numbers. We have natural number constants, we have unique identifiers, and we only have a handful of binary arithmetic operations, so we can add, subtract, multiply. We can do equal, less than, or equal, and logical and, but this choice of things is really kind of doesn't matter. We have a data type of these terminators. So we have a Coq type of terminators, which can either be a direct jump, a branch, which takes a value and two labels and gives you a terminator, and then the return operation. Here I've left off the value. That's kind of programs just halt, and the final answer could be the state. We could have added a return argument, and then we could consider that. It's not really particularly important for the kinds of proofs we'll be doing. Commands. So the only interesting thing to notice here is that there are only 5 commands in V minus, there are these binary operations. There are phi nodes, which just take a list of those phi arguments. So what's one of those? Well, it's a label paired with a value. So those are the in edge and the value assigned associated with that in edge. There are terminators, and there are loads and stores, which you load a value from address, and you can store a value into an address. And then an instruction is just a pair of one of these unique identifiers in one of those commands. So this is just literally saying that a program is going to be a collection of instructions at these unique identifiers. And to make all of our proof work simpler, we're going to kind of declaratively define the relationship between these UIDs so that we can say what are the kind of logical properties of a basic block and so on. And then we'll, off to the side, we can implement that in many different ways. Like we could represent a basic block as a list of instructions, a concrete representation. So we're going to kind of try to separate the specification of what is a good control flow graph from an implementation. This is not particularly important, but there's a bunch of useful ways of getting at the data in those commands. So for example, you can say, does this instruction use a particular, or give me the values that a particular instruction uses. So this would say, if the value, if you're adding x plus y, then it would use x and y. And similarly, which labels and what is the list of phi arguments to a phi node. These are just the destructors for the, to project out the data from the commands. Okay, so the control flow graph, as I said, is going to be kind of factored from the implementation, and we're going to just specify it abstractly as a collection of program points, which I'll sometimes use PC or sometimes P to talk about program points, because operationally these are going to be where the instruction counter can be in the program. Statically, they're just the collection of program points in the control flow graph. So what is that? Well, it's basically an offset from some label. And we can also get the label. And then we can define what it means to increment a program counter within a basic block, right? So that just means you bump up the offset from within a basic block. And we can define a total ordering on those program points within a basic block. So this is just saying that one program point is less than another if they're both in the same basic block and one's offset is less than the other. And then we can define the entry of a particular block to be the 0 offset. That's just the start of the basic of that particular block. And for any program point, it's sometimes useful to be able to say what is the beginning point of the block that this program point is in, and that's just the entry of that program program counter. And then we need to capture all of these properties of what does it mean to be a basic block, how do they connect to one another, how do the blocks connect to one another, and so on. And so we'll do that by defining a signature for well-formed for control flow graphs that I'm calling CFG here. And this is just an abstract specification. And like I said, we can implement this in a couple different ways. In the code that I'll give you, I'll show you, we have a list-based implementation, but that's not really important. So we have a predicate to say when is a control flow graph well-formed, and when is a program point in the control flow graph well-formed. So these are just abstract properties that we can then axiomatize to make our proofs simpler. We need to say what is the entry block of a control flow graph. So remember we have in this V minus, a program is a control flow graph with a designated entry block, and that's what this gives you. And then you can ask, is the program counter at a terminator in this control flow graph? So these are just the properties of interest. It could be a return, a branch, or a jump. Yeah, any one of the terminators. And then we need to kind of axiommatize the properties of what it means to be a well-formed control flow graph. So here's a parameter that says there is an instruction at this particular point, this particular program counter. It's just a relation between control flow graphs, program points, and instructions. And then we can kind of build up some properties. So for example, this UID at PC just says that there exists a command such that the instruction at the program counter in this control flow graph has that UID. So this is kind of saying abstractly relating one of these UIDs to the program points. And then we can say that the instruction, so this is just, so functional just means that this instruction at PC, if we partially evaluate it against a control flow graph, is a function from program counters to instructions. So this is just saying for each program point, there's a unique function that's defined there. There aren't two. And this injectivity just says that for every distinct program point, you get different UIDs. Okay, so this is just kind of defining abstractly the properties of these control flow graphs. And what does it mean for there to be a well-formed instruction at a particular program counter? Well, it just means that if you have the well-formed, for every program point, then there exists an instruction there. And that instruction is, there exists an instruction at that program point. So this is just saying that every program point has some instruction. And then we can abstractly characterize blocks. So we can say, well, if we are given a particular control flow graph that's well-formed, and we look at the entry block of that control flow graph, and we look at the starting instruction, the block entry of that control flow graph, well, that is a well-formed program point. And every block has a terminator, just means that in any well-formed control flow graph, for all program points, if the program point is well-formed, meaning that it's part of this control flow graph, then there exists some point later, which is a terminator. So this is saying that for any program, any well-formed program point, you can find the terminator associated with that block somewhere later in the block. That's what these two things together say. This is LE on PC is just the pointer within block program point ordering. And then this says that there are no gaps. So if you, essentially, if you have a program point that, if you have a block that has a terminator at some program point P prime, then at all of the program points prior to that terminator, there are well-formed instructions. So these are kind of abstract axiomatic characterization, then that would be enough to prove the well-formedness of all of the properties of the control flow graph of the blocks. Yeah?
So are these properties that are true because your program is in SSA, or rather do you have to prove that your program is in SSA?
So these are not yet talking about SSA. These are just talking about how do you abstractly divide code into these basic blocks that have to end in terminators and map, assign to each instruction one of these unique identifiers. We'll have to add, we're going to do a similar thing to say what are the specifications of a well-formed SSA control flow graph. That will add a bunch of other properties like the fact that these are only assigned once, and that, for example, the scope of the UIDs that you mention in any instruction is well-defined and so on. So there's going to be a bunch of other stuff we layer on top of this to get to the actual SSA. Yeah?
So what is CFG? Was it a module? Or?
So CFG is a module. It's actually a module signature, so a module type CFG. So this is just giving the spec of any any implementation of control flow graphs.
So an implementation should give an implementation for all these axioms.
Yeah, that's right. So it gives you, you would have to give the type T of control flow graphs, which in our list implementation, a control flow graph is a list of labels paired with lists of instructions. And there are various concrete ways you could implement this. You could use a map from labels to lists of instructions, for example. Not yet. That's right. So that will be a property that we talk about the well-formedness of the code. This is just talking about the structure of the that there is a terminator at each block, and we haven't even said that that exactly what you're saying that you jump. This is not well-formed. This is just a control flow graph. It's not even saying that it's meaningful code yet. That's right. Okay, so those are block properties. Okay, but this is enough to talk about the operational semantics, because all those other things about well-formedness and so on are properties that we want to rule out in a good implementation of the operational semantics. So just like in a regular ML program, you want to prove type safety, here you want to prove jump safety and fee safety, for example, that you never try to jump to a label that doesn't exist, and so on. So those are static properties that don't have to do with the operational semantics, except that, of course, you need to have those properties to be correct, right? So if you have an ill-formed control flow graph where there's a jump to some label that's not there, you want to rule it out. But you can define the operational semantics in such a way that that's a stuck state in your operational semantics, and then the soundness of your type system will show that that's.
Could you not do exactly the same for instructions that are missing something you made an axiom for well, right? So missing instructions, you get stuff.
Yeah, we could do that. So this is it's a modeling choice, yeah, I guess. Okay, so let's switch back here and talk about operational semantics. Okay, so as we saw, there are only 5 kinds of instructions: binary arithmetic, memory load, memory stores, terminators, and fee nodes. So what is the state of a V- program? So we're going to write down, we'll use small step relational operational semantics. So we want to take one of these control flow graphs and some current state and show how it transitions from one state to another. What state is there? Sorry? We at least need the program counter. Anything else? We need memory to model the loads and stores. The value of the registers. We need the value of the locals. And you might think that's all you need, but then as somebody pointed out in the back, there's this issue with atomicity of the fee instructions. So here's an interesting example of a program that is legitimate SSA, and we can think about why. So here's the idea. We have some predecessor block that just does a direct jump to this loop, and the loop is assigning 2 SSA variables, fee nodes, as it should. There are 2 predecessors to the loop block, the loop itself and the predecessor block. So there are 2 cases for the fee nodes. In the case that we come from the predecessor, we're going to assign x0 and y1. And in the case we come from the loop block, we're going to assign x, y, and yx. Okay? This is actually a perfectly well-defined program. And then we're going to compare x and y, and if x is less than or equal to y, we'll branch back to the loop, and otherwise we'll exit. Okay? So the question is, what is the semantics of this SSA program? Will it ever reach the exit, for example?
Well, that can't be true on one of those.
Right, so the first comparison, let's assume that pred is the entry point to this program, and let's assume that those ... are nothing. Then when we jump to the loop, we're going to get x is 0, y is 1, so x is definitely less than y. We'll branch back to the loop because that condition is true. And then what happens? So we're now at the second iteration of this loop. what value does x get? Well, from the loop where we should assign it y, which is, which in the last iteration was 1. And then we need to assign y x, but which x? It now seems like we have 2 x's in scope. We have the x that was defined at the point where we took this back edge, and we have the x that is defined sort of immediately before. And the SSA semantics say, well, we could pick either, I suppose, but it actually makes more sense to pick the old version of x, not the new version of x. Because that way, reordering these 2 instructions would have no effect on the program. So this, one way to think about it is we want to look at the phi nodes of a basic block and execute them atomically once at the beginning of before we do anything else, with respect to the state of the machine that was there on the control flow edge that we took into the block. Another way to think about it is, well, we just keep track of the old state. What was the state when we came in on this edge? And whenever we evaluate a phi node, we just use sort of the state at the beginning of the block from that entry. And we keep around 2 pieces of, 2 copies of the local values. Does that make sense? Okay, so these are the 2 options that I just mentioned. So one option is to require that you put them all, conceptually, you put them all at the beginning of the block and execute them atomically. In fact, that's how we originally developed all of our Vellum infrastructure. But I think this second option Dimitri discovered works out nicer for the proofs because you can treat the instructions a little bit more simply. But basically, you just keep track of the state of the local variables that you had when you entered the block, and when you evaluate a phi instruction, you just look there instead of the kind of current state that you're updating as you go through the block. So let's look at that. That's really the only tricky point of the operational semantics for V minus. Yeah?
How do we resolve the phi nodes when we do that? You have nothing in the state that lets us figure out which.
Yeah, so here's what we're going to use as our state for the V minus, right? We'll have the memory, which is a mapping from addresses to nats. We'll have the PC, which is the current program counter. We'll have the locals, the current value of the bindings for all of the SSA variables. We'll have the predecessor program counter. So this will be the program counter of the edge we took to get to this current block. And we'll also have the predecessor locals, which are the locals that were in effect at the point where we jumped to this block via that edge. Okay, so then actually once we've kind of seen that, then the operational semantics are really straightforward. To evaluate a value given some locals, we just check if it's a natural number, we get the answer, the natural number. If it's a UID, we look it up in the current map. Now, one thing to note is that this is a partial operation, so we're returning an optional nat here, and this is one of the places where our static semantics for SSA will rule out the partiality. So we're allowing this to fail, and in our operational semantics, this will be a stuck state if you try to look up a variable that's not defined. Similarly, binary operations, there's nothing particularly exciting. So to evaluate a binary operation in some current local configuration, we take the binary operation and the two arguments to it. We evaluate them. Those are both partial operations that we just saw. So if both of them give us some natural number, then we just apply the operation, so plus times whatever, and return some. And otherwise, we have some partiality, so we just fail. And here's the phi nodes. Phi nodes are actually pretty straightforward. So This locals is going to be, we'll see in the actual step that this is going to be the predecessor locals. This will be the predecessor label, and this is the association list between the labels and the values that the phi nodes should evaluate to. So we just look up the label that we came in on in the phi list, and then evaluate the associated value there. And control transfers, here again there's some partiality because the label that we try to jump to may not be in the control flow graph, right? So if we want to evaluate a terminator, well, we're in some local configuration. We are evaluating this terminator. So if it's an unconditional jump, we just say we want to jump there. If it's a conditional branch, well, we have to test the conditional. That's what this evaluate val does. And if we get some answer, we just branch to the false or true branch. And okay, so those are the bits and pieces, and then we can write down the actual small step relational semantics like this. So it's just going to be given a control flow graph and one of those machine states, what's the next machine state? And so this is a little bit dense, but you can read it like an inference rule. So to say what happens for a binary arithmetic operation, well, what we need to know is that the instruction at the current program counter, which is assigning some particular UID the result of this binary operation, well, we evaluate that binary operation using that auxiliary function we just defined, and it must give us some answer. Otherwise, this rule won't apply. This relation will not, there won't be an inhabitant here. And then, so that's, in that case, we step from this, from the state where we are in this particular configuration of the program counter, the locals, to one where we increment the program counter, and we update the locals to say that the UID that we just defined is the sum n, is the n that we computed. And we just carry through the prior location information. That's only going to come into play when we evaluate the phi nodes. Oops. Okay, so in fact, we can see that right here. So here's the phi node. So if the instruction is at a phi, and it's assigning some UID, the appropriate value from this association list, well, we evaluate the phi nodes in the predecessor local state. That's the ploc. We use the label of the predecessor program counter. That gives us the block that the predecessor jumped from. And then we look it up in this current association list. And we better get some answer there. And in this case, we just increment the PC. We update the local state with that value. And we, again, propagate this unchanged. Yeah?
How do you decide whether to write properties or functions? For some places, we could have written this step as state to state, right? But you
Yeah, we could have. Let's see. So in general, if you can write it as a function, then you can use calc to evaluate the function, and that helps in some cases in the proofs. In this case, for relations, yes, we could write this one as a function. Because it's not well-founded. So it doesn't terminate in calc, right? So this, you can write an infinite loop in SSA, and you can't prove that it terminates, which you would need to write it as a function in calc, and so you can't. So you have to write it as a relation, and then, yeah.
Okay,
Yeah.
so the answer is write it as a function unless you can't.
Pretty much, I think that's but sometimes it can be extremely tricky to find the termination metric for an arbitrary function, in which case write it as a relation and then punt on the rest of it and see if you can do your proof. Okay, So the terminators are what actually change that local state. So if the instruction is at a terminator, we evaluate, we just look up, we find out what the next block's label should be, and we step from the current state to the entry point of the successor. And here's where we change the previous, so we just copy in the current state from the current block as the predecessor state for the next block. And actually, load and store are not very interesting at all, so I'm not going to really dwell on them, but they're exactly what you would expect. For load, you look up, for load, you have to update the locals where you look up in memory the address. Here we're assuming that the memory is total. That's a simplification just to make v minus a little bit simpler, but it's compatible with the kind of imp semantics where you assume all the addresses you ever want have at least 0 or something in them, and you can always look them up. And similarly, when we do a store, we update the memory at that particular address with the value. So that's the operational semantics. And actually, that's a very good place, I think, for me to stop today. We didn't quite get to the static semantics, but I'll do that tomorrow. And then we'll pick up with proving transformations on SSA forms. Are there any questions about the operational semantics? Yeah. Sorry. That's true. In LLVM, the entry basic block does not. Yeah. So we could define it to be itself, or so that we could have made the predecessors of the entry block optional. Actually, no, that's not true. We don't.